So last time we were trying to solve this equation. So we have V0y is gy, and so here you have vt, dy, here you have dy. All right, and then you're going to have a boundary condition which is vt1 is vte, and this is 0. Right, so this is the equation that we were trying to solve last time. So this is a PD, right? So this is a PD because this is partial differential equation. Because you have two variables, t and y. All right? This is a partial differential equation because you have two variables, t and y. Because t is first, so derivative in t is first order. So you have only one initial condition, right? T is equal to 0. All right? So because the derivative in t is first order, so for t you only need the initial condition. So now for y, we have second order derivative. So you have boundary condition. And y is equal to 1 and y is equal to e. Explain again. So last time we were trying to solve a partial differential equation. This is a partial differential equation because you have partial derivative in t and partial derivative in y, right? So in t you have one derivative, so you only need one boundary condition, and because this is one boundary condition, you call it initial condition. All right? Now, for y, you have second order condition. So, so in y you have second derivative, so you have two boundaries, y at 1 and y at e. So the method that we were trying to use last time was the splitting, right? Or separable. We write v as the product of t times capital V, right? So then you're gonna replace the derivative in of v minus dy of v minus y dt of v to be 0 can be written like t prime times v minus y squared times v second times t minus y times t times v prime, and this is 0, right? And after arranging the term, you gonna arrive at t prime over t is y squared v second of y plus y t v prime over v, and you're gonna arrive as an eigenvalue problems. All right? I explain again. So here you have a partial differential equation. You have two conditions: initial condition for t and boundary condition for v. All right, for y. So what you do is you use a separate method. You split v to be the product of t and v, in which t is a function of t and v is a function of y. You plug it back to the equation. You do a computation with this new ansatz. Then you get that t prime over t is equal to y squared v second plus y v prime. Yes?
What are the circumstances for v equals the product of those two?
What is the circumstance?
You said there's a theorem for it,
Yes.
but what are the requisites for that theorem?
So so in this case, you are solving it on a square, right? So the domain has to be on an interval AB, right? This is the first thing. The second thing is that the coefficient of dy, the second derivative in y and the first derivative in y, that depends only on y. They don't depend on t. So then you have the t minus ay dy of v minus by dy of v is 0. All right, and you have the same boundary condition, right? So if you have derivative, you have t here and t here, you won't be able to use it. But the problem is much more difficult. All right, so and then this is called the degenerate parabolic equation, and the problem is still open up to now. I mean, it is solved for several cases, so people understand quite a lot about this equation. But I mean, if you have a t y, right, b t y, but you have to have condition for a and b so that this equation has solution, right? So it could happen that the solution is blow up in finite time, so you don't have solution like this. Well, this is gonna be advanced PD class. All right. So now when you write, so here you can do separable because this is simple. So you write v as a product of t and b, right? And then you can separate t and y, right? So in this case, you do this algebraic ansatz and you can separate them. So this is an easy equation. So because on the left-hand side, you have a function of t, and on the right-hand side, you have a function of y. So this has to be a constant, right? So this is function of t. And this is function of y. So this has to be a constant, right? So now everything comes back to an eigenvalue problem, right? So we're gonna have to solve y squared v second plus y plus lambda yv prime plus lambda y is 0, and t prime plus lambda t is 0. All right. So now going to the boundary condition, you have what? You have v of t 1 is v of t is 0, meaning that capital of 1 is equal to capital of E, and this is also 0, right? So after you do this and that, you get a system of two equations, one for t and one for t prime. All right. So now you have to identify the boundary condition for this system. So you use the boundary condition of the equation, and you find that the boundary condition for V should be 0 at 1 and E, right? Right. So now this is what we discussed in the previous class. So let us continue with today's class. So we have to solve y squared v second plus y v prime plus lambda y is 0, and y at v at 0, 1 and v at E is 0, and this is the midterm tree, right? So you find v y to be sinus of n pi log t log y, and you find that lambda is n pi squared. All right? It's clear? So after I explain again, now you have to solve PDs. So the method that you want to solve, that you solve the PD is to use this ansatz, right? So you suppose that V is the product of T and Vy. You plug it back, and then you get an eigenvalue problem. Now you have to solve the eigenvalue problem. So the eigenvalue problem is already solved. So you already know that the eigenvalue will be n pi square, and the eigenfunction will be sinus of n pi log y, right? So here I'm gonna write like Vn and lambda n, and I'm gonna plug it back to the first equation, right? So coming back to the first equation, coming back to t. So I'm gonna have t prime. So here I have n, so I have tn prime plus lambda n of t is 0, and I'm gonna put some tn as 0 to be a constant cn. All right. This is the initial condition that we use because, but we still don't know what about initial condition that we should use, right? Now, we come back to t, right? So the eigenvalues will be n pi square. So I plug this eigenvalue into the second equation. I have t prime. So here I have tn prime plus lambda n. T is 0, and I'm gonna need some about initial condition, right? Right, so let us try to solve this equation. So you have tn prime plus lambda n t 0. This is a first order differential equation. How do we solve it? It's exponential. Yes. So this is, can you sign it? I forgot a paper. Do you have one paper? Can you sign the back of the paper, please? So this equation has an exponential solution. So you have tn prime is equal to lambda n tn, right? So which means that tn prime over tn is minus lambda, right? So this is log of tn prime is minus of lambda, because this is equal to this, right? This means that log of tn is minus lambda t plus a constant c0, some constant, right? So which means that tn will be exponential of minus t times e to c0, and this is c e to the minus lambda t. All right? This is tn of t. Right, so I explain again. After I found the eigenvalues for the equation for v, which is n pi square, I plug it to the first equation, and tn prime plus lambda n t, tn is 0, with some initial conditions cn that we will identify later. All right? So I have what? I have tn prime plus lambda n, tn is 0. This is the first order differential equation, and we solve it several times in our class. So you have t prime is minus lambda n tn. So you divide both sides by tn. So you have t prime over t is minus lambda, right? But t prime over t is log of t prime. So you have log of t prime is minus lambda. So log of t is minus lambda t plus c0, right? So you take the exponential on both sides. You have tn of t is minus exponential of minus lambda e to the c0. C0 is some constant, right? So I can put this with c to the minus lambda t. Questions? Now I have the initial condition, right? So I have t0 is cn, which means that c is cn. So I have tn will be cn e to the minus lambda n t. All right? This cn is some initial condition that I have to find. Right? Questions? So I explain again from the beginning. So in order to solve this equation, you suppose that the solution is the product of a function of t and a function of v. You plug it back to the equation. You plug it back to equation. You split v and t. All right. So now you solve for v. You solve for v, and this is basically an eigenvalue problems. And lambda n is n pi square, and vn will be sinus of n pi log y. Right. Now you have this lambda n is n pi square. You plug it to the equation for t. You solve it. So this is the first order differential equation. You can solve it easily, right? So you have Tn prime plus lambda n Tn is 0, which implies that Tn prime is minus lambda n Tn. And this means that Tn prime over Tn is minus lambda n. Sorry. So Tn prime over Tn is log of Tn prime. So you have log of Tn is minus log of minus lambda n t plus constant c0. You solve it and you find Tn is Cn e to the power minus lambda n t. Right? Questions? It's clear? Now you have Tn and you have Vn. You have to go back to the solution, right? What is the solution? So the solution will be Cn. The solution be e to the power minus lambda n will be Tn times Vn be y, and this gives you Cn e to the power minus lambda n t. All right, sinus of n pi log y. Right? So you have a series of solutions. What you do is you have to sum all of them. So I explain again. So here I find one sample, and here I have one Tn. I have one Tn, right? So what you do is you multiply all of them, right? But again, you have to sum all of them because everyone is the solution, right? So you're going to have to sum all of them. So you have the sum when n is going from 1 to infinity, and this is when n is going from 1 to infinity, and this is basically the solution. All right? So we need to take a sum, right? We have to take a sum. All right? Now, the job now is to find Cn. So how do we find Cn? We need to identify. Right? So how do we identify Cn? We have one thing that we haven't used.
If we go back to the boundary condition, v
Yes.
0, y.
Yes, can you stand up? I can take one, please. So we have to use the condition, which is the initial condition of v0y is equal to gy. Right? This is something that we never use. So v0y will be the sum when n is going from 1 to infinity of Cn e to the power minus lambda n 0 sinus of n pi log y. So this is 1. So this is gonna be the sum when n is going from 1 to infinity of Cn sinus of n pi log y. And this is gy. All right? I explain again. So after you found Vn and Tn, so you have to take the sum of all of them, right? So this is what we did in the previous case as well. When you have all of the eigen values and all of the eigen functions, you have to take a sum with some constant, right? So So V will be the sum of Tn and Vn because each of them is the solution of the equation. So you have Cn e to the power minus lambda nt, and here you have sinus of n pi log y. Now we have to use the initial condition. You have V of y0 is gy, right? So I'm gonna plug 0 into this expression, and I want to see what is going on. So I'm gonna plug 0 here, and so I have e to the power minus lambda times 0. This is 1, so this goes away because it is 1. So I have Cn sinus of n pi log y is gy. Right, so what is Cn now? Cn will be the coefficient in the expansion of G in terms of this basis, right? So Cn is the coefficient in the expansion of G on the basis sinus of n pi log y. All right. So we computed this already in our previous class, right? Do you still have the Cn and this one? Can I see the paper? Right, so we computed this already in the previous class. All right, so Cn is 2 over n pi squared sinus of n pi over 2 minus 1 over n pi cosine of n pi over 2. Right. Right, so you remember this coefficient, right? So I explain again. So to find a solution, right? To find a solution, you have to multiply Tn and Vn, and you're gonna take this up. So you're gonna have the sum when it's going from 1 to infinity of Cn e to the power minus n pi sinus of n pi log y, right? So we need to know what is Cn. In order to compute Cn, you're going to use the initial condition. The initial condition says that V at 0y is equal to Gt. Gt is log of y, right? For y is going from 1 to square root of e. And this is 0 when y is going from square root of e to e, right? This is the function that we have. So you have V of y0 is gy. Gy takes this form, right? Now you have you're gonna replace 0 here. So you're gonna have V0y is Cn times 1 times sinus of n pi log y, and this gives me Cn sinus n pi log y. So you have the sum of Cn sinus of n pi log y, which is gy, which means that this Cn will be the coefficient of sinus of n pi log y in terms of G, right? So Cn will be the expansion of G on this basis, and the expansion of G on this basis is computed in the previous class, right? So Cn will be this one. It's clear? Any questions? So you know how to solve a PD, right? So a PD is simply a general way. So you have when you solve a PD, you have to apply the method that you solve ODs to PDs, and this is gonna be the same thing. I mean, this is the same concept if you go to graduate classes or you go to PhD. It's gonna be the same thing. You have to start with the simplest one, and if you expect something that works for the general case, it has to work at the simplest case, right? Other questions? It's clear? Alright, so if there's no questions, we're gonna go to another example, which is one example in the book. Right, so this is an easier example in comparison with what we have in the book. So you have what? You have the heat equation, Uxx. You have boundary condition, you have Ux. The equation is solved on 0, 1. X is in 0 and 1. And t is from 0 to infinity. Ux and 0t will be 0. And U1t will be 0. And U1 at 0. U0t, Ux0 will be x. So this is the boundary condition at x is equal to 0. And this is the boundary condition. So boundary condition at x is equal to 0. So you have u 0t is 0. So boundary condition at x is equal to 1. You have u 1t is 0, and initial condition and t is equal to 0, you have ux 0 is x. Right? You have three conditions. 1, 2, 3. Alright, so I explain again. You have the heat equation, which is ut is uxx. Right? So the derivative in time of u minus the derivative in x of u is equal to 0. The equation is considered on 0 to. Alright? The time will be from 0 to infinity. The boundary condition, so here x has two derivatives, right? So you have two boundary conditions at 1 and 0. So you're going to have u at 0t is 0. The other boundary condition at x is equal to 1 is u1 of t is equal to 0. So the initial condition is as t is equal to 0 will be ux. 0 is x. Right? It's clear? So how can we solve this equation? This is easier than what we have in the previous exercise. How do we solve this equation? This is the PDs, right? And this is easier because you have only one term uxx, right? In the previous one you have y squared uyy and plus y uy, right? Here you have only one term. So how do you solve this equation? Can you agree? No, you're going to use the same method. You're going to use this and that, right? You're going to use the separable method. The form is a little bit different, right? So the previous equation and this equation is the same. You're going to have utx is tt times vx, right? So it's going to be the same ideas. So for the previous equation, you do the same thing, right? So you have utx is tt times vx. So now what is ut? Ut will be the derivative in time of this function, right? So and this gives you t prime. So ut will be the derivative in time of tt times vx, and this is t prime Vx. All right? So I suppose that the solution is separable. So you have utx will be the product of tt times Vx. All right? So ut will be dt of tt times Vx, and it is t prime t Vx. So you're going to have uxx will be the derivative in x of tt Vx. All right? And this is tt v second of x. All right? It's clear? Now I'm going to plug everything back into the equation, right? So you have ut is uxx, which means that t prime in t times Vx is equal to tt times v second of x. All right? It's clear? So I explain again. We're going to use the same method. You have utx will be ut times Vx. So the derivative in time of this guy will be dt of ut times Vx. And this gives you t prime Vx. All right? Now I'm going to take the second derivative in x of u, and then I get uxx will be dxx of tv. And this gives me t times v second of x. All right? So now I'm going to plug back to this equation. I'm going to have ut is uxx. All right? Which means that you have t prime times Vx is tt times v second of x. Right? Questions? So this is basically the same idea with the previous exercise. All right? So now you have t prime of t over tt is equal to v second of x over Vx. Right? So I'm going to divide Vx to the other side and t to this side. So I'm going to have t prime t over tx is equal to v second over v. Right? Questions? So this is the function of t, and this is the function of x. A function of t is equal to a function of x. This means that they have to be constant, right? So this is a function of t. And this is a function of x. And they are equal, so which means that here you have a constant. Right? It is going to be the same thing, right? I explain again. To solve this equation, all right? To solve this equation, you have ut x is tt times Vx. All right? So now you're going to take the derivative in time of u. The derivative in time of this product will give you t prime Vx. You're going to take the derivative in x of u, and this gives you tt times v second of x. All right? The equation is ut is equal to uxx. So ut is t prime Vx, and uxx is tt times v second of x. All right? Now I'm going to divide t over here and v over there, and I have t prime over t is v second over v, and this is minus lambda, because on the left hand side you have a function of t, and on the right hand side you have a function of x. All right? So these two functions are equal, which means that you have to have a constant. Now you're going to solve it. So you have what? You have t prime of t over t is minus lambda, which means that t prime of t is minus lambda tt. And this means that t prime of t plus lambda tt is 0. All right, so this is exactly the same as the previous equation. So the equation for t will be a first order differential equation. You have t prime over t is minus lambda, which means that t prime over t is minus lambda t, which means that t prime t plus lambda t is 0. All right? Questions? Now you're going to solve the second equation, right? You have what? You have v second of x over vx is minus lambda, which means that, so this is example 4.5.1, but it is a little bit easier, right? So you have v second over v is minus lambda, which means that you have v second is minus lambda v, and this means that v second plus lambda v is 0. All right? So you also decouple the equation into two boundary value problems. Questions? Right, so I explain again. So you have ut, x is tx times vx, right? You take the, so in the equation you have ut is uxx, which means that you have to compute ut and uxx. Ut will be t prime v, uxx will be the second derivative of this guy, and this gives you t times v second, right? Now you're gonna put ut here and uxx here. You have t prime v is equal to t times v second. So you divide here t and you divide here vx. You're going to have t prime over t is v second over v. And because on the left hand side you have a function of t, and on the right hand side you have a function of x, they have to be constant. Right? So the first equation, t prime over t is minus lambda, give you t prime plus lambda t is 0. And the second equation, v second over v is minus lambda, give you v second of lambda v is 0. Right? And this is an eigenvalue problem. Right? This is eigenvalue. All right? Questions? So what is the next step to solve the eigenvalue problem?
Boundary conditions.
Boundary condition. Yes. Can you stand up back, please? So boundary condition, right? So you have what? You have u 0t is 0. So this is the boundary condition here, right? So this is x equal to 0. So which means that tt times vx is v tt times v0 is 0, which means that v0 is 0. So you have u of 1t is 0, which means that tt v1 is 0, which means that v1 is 0. All right? So this is the boundary condition 1, boundary condition 2, boundary condition 3. So boundary condition 1. This is boundary condition 2. Right? So the first idea is to introduce this as a square. You have u is t times v. T is a function of t and v is a function of x, right? You plug everything back into the equation. You decouple the equation. You have t prime plus lambda t is 0, v second plus lambda v is 0. Now you try to find a boundary condition, right? The first boundary condition, u at 0t is 0, gives you tt times v0 is 0, which means that v0 is 0. Tt cannot be 0, because if tt is 0, u will be 0, and you have a 0 solution, right? Similarly, you have u at 1t is 0, which means that t1 times v1 is 0, which means that v1 is 0. Tt again cannot be 0, because if tt is 0, this u is 0, and you have a 0 solution, right? All right, so now we have a system to solve. You have v second plus lambda v is 0, with v0 is 0, and v1 is also 0, and you have t prime minus plus lambda t is 0. So this is x, and this is t, with some initial condition cn that we gonna try to figure out later, right? Questions? I explain again. So first step, is to split the solution into the product of tt times vx. All right? When you plug into the equation, when you plug everything into the equation, you're gonna find two equations. The first one is the equation for t, and the second one is the equation for v. Right? So this is the key step. And after you plug into the equation, you're gonna have all of these things. Now the next step is to find boundary condition for v, because you're gonna solve the boundary value problems, the eigenvalue problem, and so this is why you have to find those boundary condition, right? Now after you have the boundary condition, you have to solve this system, right? All right. Now let us try to solve this equation. Yes?
Does V have to be linear in X?
V have to be linear in X?
Because
What do you mean by linear in X?
Well, you have U of X comma 0 equals X, and T equals a constant. So doesn't that mean that the other one?
Okay, so we are all doing linear function, linear equation. We haven't done any non-linear equation, right? So if you want to do this and that, the equation has to be linear, right? So in this class, we haven't done non-linear PDEs. Non-linear PDEs is something other, right? All right, questions? So what do you mean by non-linear?
Well, like the solution for V of X?
Solution for V of X, yes?
Yeah, it has to be some multiple of X, right?
So this, you mean this eigenvalue problem?
Well, you have U of X comma 0 equals X,
U of X,
right? That's your initial condition.
and this is initial condition, but
Yeah.
this,
And
this,
that's- and U is a product of T and V of X, right?
right. So U will be, yes, this is a very good question. So what you do is you solve for lambda n and Vn, right? So when you solve this equation, you find lambda n and Vn, right? So you have lambda n and Vn, and then you can find Tn, right? So you're gonna have this. So U will be, because they're all solutions. They're all solutions. You have to take the sum, right? Tn times Vn. And now you match with this initial condition, right? So you have to find a constant of Tn so that this sum is equal to x when t is 0. Right? It's clear? Right, so, all right, so let me try to summarize the big picture for you, right? So now let me summarize this part, that we have two equations, right? And then we have to solve these two equations. It's clear? So the big scheme will be the following. All right, so you have dt of u is uxx, dxx of u. Right? Step number 1, you have utx will be tt times vx, right? And then you plug this into the equation, right? When you plug this into the equation, you're gonna have two equations. You have t prime plus lambda t is 0, and you have v second of x plus lambda v x is 0. All right? It's clear? So the first step is that you split 2 into t times v, right? So you plug into this equation and you found these two things, right? Now you solve the second equation. So solving equation capital 1 and this is capital 2. Step number 2, you solve the first equation, right? And the second equation. When you solve the second equation, you're gonna find lambda n and phi n. You're gonna find the eigenvalue and eigenfunction. All right. So you have phi n second plus lambda n, phi n is 0. All right. This is what you're gonna find in the second step. The next step is that you have to plug this back to this one, right? But to, so you plug that back to the first equation, and you're gonna find step number 3. All right. So you have Tn prime plus lambda nt is 0, which means that Tn t will be Cn exponential minus lambda nt. Right? It's clear? So in those, all of these things, phi n and Tn, they are solution, right? Step number 4, you're gonna take the sum of everything, right? You're gonna have Tn times Vn is phi n is one solution. One solution. Right? Let me put C to be 1 so that you don't have to worry about C, right? Let me choose the initial condition to be 1. So this Tn is also one solution, right? So U will be UTX will be the sum of Cn Tn times Vn. All right. So this is going to form a basis for the solutions, right? So this is one component which also satisfies the equation, but there's several of them, so you have to multiply all of them with a weight Cn. It's clear, right? So the solution will be Cn e to power minus lambda n Vn of x. This is the solution, which is a linear combination of all of the terms in the basis. This can be seen as a basis. This is the basis. So how do you find Cn? How do you find Cn? You're going to use the initial condition, right? So you have x is u at u0xt, which is Cn e to power minus lambda n times 0, Vn of x, and this gives you Cn Vn of x. So basically, this Cn will be the expansion, the coefficient of the expansion of x in terms of the basis Vn. It's clear? We still have 2 minutes, right? It's clear? Yes?
So with the Cn, that's just defined by based on what you your initial condition is.
Yes,
so
the
the
Cn
previous
is
problem, it was that full expansion because it was a function. But in this problem, if you just set it to equal 1, if like, what's the value? If y is 0, comma y is equal to 1, then Cn equals 1.
No. If this is 1, this Cn is the coefficient of the expansion of the function 1 on the basis.
Okay.
So this is still an expansion.
Okay, so it's still an expansion on that. Okay, gotcha.
So expanding n. So after you do the splitting, right? So after you separate the two variables, you have two equations. The first equation is the eigenfunctions equation, right? The eigenfunction equation gives you one basis Vn on the x, but this is only the basis for x. Now you still have the t, right? You have two variables. So the basis for t will be e to power minus lambda nt, right? Which is the solution of this guy. So you multiply Tn and Vn, and you're gonna have a basis for t and x, both, right? So the solution will be an expansion on this basis. So you have Tn times t and Vn, which is the basis for t and x. All right, but you have to compute this Cn. So how do you compute this Cn? You have that when t is 0, u of 0x is equal to x, for instance. So you put 0 here, and this is going away, so you have Cn, Pn. So basically this Cn will be the coefficient of the expansion of the initial condition on the basis, but the basis for x, right? Pn. It's clear? Right, so I try to explain clearer next Friday. This Friday, right?